This is the seventh and last section in the sequences and series chapter, and this is about recurrence relations. Now, a recurrence relation is a bit like something that we call iteration, where we have some sort of rule. So let's say we've got a function, a function of a term. We do something to a term, and then you've got some sort of starting value. So let's call that u1. It might be u1, it might be u0, and we put it into this function, and out comes u2. And then you take that answer and you put it back into the function, and then the next one that comes out is u3, and then u3 goes back in and you get u4, and so on. So you use the last term to get the next term. Now I've put here, how does a recurrence relation differ from an nth term rule? Well, an nth term rule, you put the term number in to get the term. With a recurrence relation, you put the last number in to get the next term. So you always need the last one to get the next one. Now, sometimes when we write a recurrence relation out, it is possible to convert it into an nth term rule, because you might see a pattern, or for an arithmetic sequence or a geometric sequence. So actually what we might find is this recurrence relation produces an arithmetic sequence or a geometric sequence. That's possible. Sometimes it doesn't. It may produce a nice pattern, but it may not necessarily be a pattern that we can write a rule for. It all depends on it. Now, whenever the next number comes out here, I suppose what we could do is we say that we get up to, the next term's always going to be un plus 1. So I'll just rub those out to give myself a bit of space. So un plus 1 is going, in general, is the next term. Yeah. Here we're just asked to write out the first 4 terms of the following sequences. So you can see you're given the starting value and you're given the rule. So you have to work out one at a time. So u1 is 7, that's given. u2, well, you take u1 and you add 4 to it. So it's going to be the last term plus 4, which is 11. u3, well, that's just going to be the last term, 11 plus 4. So you can see the rule up here. It basically just says take the last term and add 4 to it. Is 15. And u4, that's going to be 15 plus 4, 19. So there we go. The first 4 terms, 7, 11, 15, 19. 7, 11, 15, 19. Part B, slightly different rule, different starting number. So this time u1 is 5, and it's the same rule as the last one. It's taking the last number and adding 4 to it. So it's going to be 9. u3 is going to be 9 plus 4, 13. u4 is going to be 13 plus 4. So because we have a different starting number, our sequence is slightly different to the last one, in that it's just 2 lower, because the starting number was 2 lower than that one. Okay, nice, easy, basic stuff. 5, 9, 13, 17. So here what we have is some information. We're given the first term. It's given algebraically as p. And we're given the rule here. Yeah, here's our rule, and there's some information about p and n. N is greater than or equal to 1. P is less than 0, so that might tell us something about our solutions. And it says show that A3 is that expression, right? Well, we'll start with A1, which we're given, which is p. Now to get A2, I plug this into the recurrence relation, so that's going to be A1 squared, so p squared minus 1. Then I take that and put it in again, so A3 is going to be the last value squared, so that's p squared minus 1 squared minus 1. It's just given in a different form, so I'm just going to expand the brackets. So that'll be p to the power 4 minus p squared plus 1 minus 1. So yeah, I can see I'll get p to the power 4 minus 2p squared QED. Right, part B, given that A2 equals 0, find the value of P. Right, A2 is this one, and we're told that that equals 0, so that means that P squared minus 1 equals 0, which is P squared equals 1. Now, P could be plus or minus the square root of 1, but up here it said that P is less than 0. So actually we'll write down that P is plus or minus 1, but then we'll say since P is less than 0, P equals negative 1. So that piece of information was there for a reason. Okay, part C. Part C. Find the sum of these 200 terms of AR. So we're going from R equals 1 to 200. Now, since we've already worked out the value of P, we can actually, you know, I said that we'd normally use this to write out the first 3 terms. Well, we've got the first 3 terms over here. So let's just substitute negative 1 in and see what we get for the first few terms, and we can use that to help us decide whether it's arithmetic, geometric, what the first term is, what the common difference or common ratio is, how many terms. Well, terms are 200. Right, so A1, the first term, is going to be negative 1 because P is negative 1. A2, the second term, well, that's just going to be negative 1 squared minus 1. No, actually we're told that it's 0, isn't it? And then the third term, A3, well, that's going to be negative 1 to the power 4 minus 2 times negative 1 squared. So that is going to be 1 minus 2, which is going to give you negative 1. Now it looks like this sequence is going negative 1, 0, negative 1. It looks like it's this what we call periodic pattern. Now, just to check that, I'm actually going to work out what A4 is, and I'm expecting A4 to be 0. Now, this will require a little bit of work. So A4, not A to the power 4. A4, that's going to be our last A3 squared. So I can just now put the numbers in. So A3 squared, which is negative 1. For A4 minus 1, so that's going to be 1 minus 1, 0. Then the next one is going to be that squared minus 1, so it is a periodic pattern that goes like that. And in fact I could have saved myself a bit of time and I could have actually just put the numbers straight into there, yeah, because the next term is just the last term squared minus 1, so I could have saved some time there. Surprised no one said anything. Right, so if I'm adding up these 200 terms, it's actually going to be, it's not geometric and it's not arithmetic, it's this pattern. Now, what am I going to have with this? I'm going to have 100 terms of zeros, so I'm going to have 100 zeros, and I'm also going to have 100 negative ones in this pattern that goes 1, 0, 1, 0. So what's the sum of that? Well, it's just negative 100. So I didn't really need to do any working as such for that. I just needed to realize that this pattern is like what we call a periodic pattern. And in part D, what we have is, it says write down the term the value of term A199. Now, what do I notice about this pattern? -1, 0, -1, 0, so on. Okay, well, all the odd numbered terms, so A1, A3, A5, and so on. Oops, A5. I said 5, I wrote down 3, not sure what that's about. They're all -1. Yeah, where that little subscript is odd number. Where that little subscript is an even number, so A2, A4, A6, they're all going to be zeros. Now we've got a subscript with an odd number, 199. So that's going to be -1. So we just write that down. -1 is no real working that we have to do for that. So let's just highlight that. Now you should be in a position where you can do exercise 3G on pages 80 to 81. So you want to pause it now, have a go at that. But this video continues because there is more in this section which we're going to continue and have a look at. This is the second part of this section, and I think it's pretty straightforward. So we're looking at increasing sequences, decreasing sequences, and periodic sequences. So let's start with increasing sequences. So I'm going to write the stuff at the top of my own words. If a sequence is increasing, then basically the next term in a sequence, which is basically UN plus 1, the next term is always greater than the previous term. So that means it's always greater than UN for an increasing sequence. If a sequence is decreasing, then the opposite is true, and that is that UN plus 1, which is the next term is always less than the previous term. So it's going down. Each term is less than the last. So UN plus 1 is always less than UN. So that's increasing, decreasing. Now we have what we call periodic sequences, and this is where the terms go around in a cycle. The terms go round in a cycle. Okay, and shouldn't really be a comma. The length of the cycle is called its period. So here's an example. 5, 7, 3, -2. 5, 7, 3, -2, and so on. This has a period of 4 because there are 4 digits or 4 numbers in that cycle before it repeats. So this has got a period of 4. And we know that, for example, if this is U1, U1 is going to be the same as U5 and then the same as U9. So if I add on the period to the first term, so if I add on the period to that subscript, I get the next term that's the same. If I add on the period to that subscript, I get the next one that's the same. So for example, U3. Now, which other term is going to be the same as that? Well, I add the period of 4 onto that subscript, so that should be U7, which is that one there. And then add that period on again, the next one will be U11. That's what this bit down here is all about. Yeah, basically saying if you've got a term, if you add on the period to it, you get the next term, which is the same as it, which is sort of what we've basically done down here. Okay, each one of these we just need to state whether they're, and state just means you don't really need to do any working, you just need to look at it and decide whether it's increasing or decreasing. So the first one, part 1, It's increasing because we start with 7, you add 3, you add 3, you add 3, so I can see that's increasing. The second part of the question, if the series is periodic, it's not applicable, it's not periodic. NA. Right, part B, let's see what's going on here. Right, so we start with a half, then we square it, you get a quarter, you square it, you get 1/16, you square it again, you get 1 over 256, I think, something like that. So it's decreasing. Each fraction is smaller than the last, so we don't need to write terms out, we can work this out in our heads. So this is a decreasing sequence. Again, part 2 of the question is not applicable because it's not periodic. I reckon C is periodic. That's the one we haven't used yet. So this is basically what's happening to sine every 90 degrees. So sine at 90 is going to be 0. Then, well, let's write it down. So sine 90, might be worth writing this down, is 0. Then when n is 2, it's sine 180. And sine of 180 is 0. Sorry, sine 90 is 1. What am I talking about? Why didn't anyone say anything? So sine 90 is 1. Another 90, sine 270. So this is 3 times 90. That's going to be -1. Sine 360. This is going to be 0 again. And then we're going to get back to 1. So this is a cycle that goes 1, 0, -1, 0, 1, 0, -1, 0. So this is periodic. So part 2, write down the order. Well, the order of it is 4. There's 4 numbers in this repeating pattern. Now I know the 0 gets repeated here and here, but the complete cycle isn't finished until we get here and then we repeat it. So the order of this is 4. So order equals 4. Right, you should now be able to do exercise 3H on pages 82 to 83.